Okay, welcome back to this course on signals and system. We will start with a new topic, that is frequency analysis. Frequency analysis of signals. Okay, this is a very major topic in signals and system course, and we will devote or we will focus more on this topic. This topic itself, the frequency analysis, it has two parts. One is your Fourier series, another is your Fourier transform, and again this Fourier series, it can be for continuous signals, continuous time signals, or discrete time signals. So you have continuous time Fourier series, and then you have discrete time Fourier series. Okay, similarly the Fourier transform can be for continuous time, or it may be for discrete time. So either you have continuous time Fourier transform, or you have discrete time Fourier transform. Okay, so whether you have continuous time Fourier series, then you have discrete time Fourier series, depending upon whether the signal is in continuous time or discrete time. And similarly, when you apply the Fourier transform, it can be for continuous time signals CTFT or discrete time signals DTFT. Okay, and all these transforms, they basically come under this heading of frequency analysis. And you will see in the advanced courses, like when you study digital signal processing, there are other transforms in this also, like we have DFT, discrete Fourier transform, which is basically obtained from DTFT. That is also a part of frequency analysis. Okay, and then there is an algorithm for computing DFT in a very efficient way, that is called as fast Fourier transform, FFT algorithm. Okay, that you will study in higher maybe courses. Or even there are some more advanced transforms, like we have discrete cosine transform, DCT. Okay, there is discrete wavelet transform, and so on. So many transforms are there. So we will basically focus on the Fourier series and the Fourier transform mainly, and that too in detail for continuous time signals, continuous time Fourier series and continuous time Fourier transform. Other transforms maybe in the discrete time you will study in your DSP course. Okay, so what do you mean by, first thing is, what do you mean by this frequency analysis? Or you can also say it as spectrum analysis. Okay, and there is one more term that is called as spectrum estimation or frequency estimation. There is a bit difference between these two terms. So frequency analysis means, like suppose if you take a general example, you know that white light contains 7 colors. Okay, but how you decompose this white light into 7 colors? We pass it through a prism. Okay, when you pass light through a prism, at the output of this you get a band of 7 colors. Okay, that you know. violet to red. So this band of 7 colors, we call it as spectrum of light. Okay, because each color has a different wavelength or a frequency, right? And then if you pass again these 7 colors through a inverse prism, if you pass these 7 colors through inverse prism, what you get at the output is again the same white light. Okay, now in analogous to this, if you have a signal xt and you want to find the spectrum of the signal, okay, so when you want to find the spectrum of the signal, it means you try to find out the frequency content of the signal. Okay, what are the various frequencies present in the signal, right? So what we do, we pass the signal through a mathematical tool. So in place of this glass prism, you have a tool here which is called as Fourier series or Fourier transform. So if you pass a continuous time signal or even a discrete time signal through a Fourier series or a Fourier transform, which is a mathematical tool to find the spectrum of the signal, what you get at the output of this is the frequencies in the signal. Okay, so this Fourier series or Fourier transform will extract the frequencies which are present in this signal. Okay, and by frequency, what you mean a complex exponential signal or a pure sinusoidal signal. This is what is a frequency, single frequency with the frequency of omega naught. Okay, it means if I apply Fourier series or Fourier transform on any signal, the output of that will give you signals in the form of complex exponentials only or in the form of sine and cosine functions, which we term as the frequency analysis. And if I pass all these frequencies back through inverse Fourier series or inverse Fourier transform, what I will get at the output is the original signal xt. Okay, so the role of this glass prism is basically played by the Fourier series or Fourier transform, and the role of this inverse prism is played by your inverse series or inverse transform. Okay, so this is a very general concept. In any transform, what you do, you transform a signal from one domain to another domain. So in the frequency analysis or in the Fourier series or Fourier transform, we basically transform a signal from time domain to frequency domain. Okay, this is what is done by frequency analysis, Fourier series or your Fourier transform. It converts a signal from time domain to frequency domain. It means the input to this is a continuous time signal xt. When you apply the Fourier series or the Fourier transform, what you get at the output is the frequency domain analysis. It means you basically get the various frequencies which are present in the signal. Okay, and if you apply the inverse transform, inverse Fourier series or inverse Fourier transform, you will get back the original signal from its frequency content. Okay, and this is very important that for every transform there must exist a inverse transform, otherwise that transform has no value. Okay, and why these transforms are important? When you transform a signal from one domain to another domain, okay, So in after this transformation, there is what we apply signal processing here. Okay, you apply some sort of signal processing either to compress the signal or to maybe enhance the signal or to remove the noise from the signal, and then you apply the inverse transform, you get the filtered signal, what you can say. Like suppose in the glass prism case, if I pass white light through a prism, I get 7 colors. Out of those 7 colors, if I pass suppose only 5 colors and I remove 2 colors, what I will get at the output is not white light, because we have discarded 2 frequencies. Okay, this is how filtering is done. So you pass a signal through Fourier series, you get the frequency content, and in those frequencies, some of the frequencies they are stopped while passing the frequencies to the inverse series or inverse transform. Okay, so those frequencies may be the noise components. So you remove the noise components, and what you get at the output is a filtered signal, which is noise free. Okay, similarly, you may want to compress a signal, like say when you will study and this transform DCT, discrete cosine transform. It is a very important transform which is used in signal compression or in image compression. Okay, your JPEG uses DCT for basically compression. Okay, so what you do, you have a signal, one-dimensional or a two-dimensional signal, maybe image. You apply DCT on this discrete cosine transform. This signal is transformed from now space or time to frequency. And in the frequency domain, we process it. Means if it is a suppose 16 cross 16 matrix image, output is also 16 cross 16. But this transform has a property that the energy, which is called as energy compactness. It means most of the energy in this input image, it is basically concentrated in only few coefficients, only few pixels. They will contain the energy. Rest of the pixels, they have their you can say intensity is very small in the frequency domain. So you can simply delete them. So you can store this information using few samples only. This is how your image is compressed. And then if you apply IDCT, you will get back the original image. Okay, so where is the compression technique used? That after this transformation, the matrix that you are getting, you are storing only few information in that. As a result, when you apply IDCT, the recovered image will not exactly be same as the input image. There will be some errors. But if you don't apply any processing in the DCT domain and you directly apply inverse transform, you will exactly get the same input image. Okay, and the same is in the Fourier transform. So you apply a signal, you have a signal, you apply Fourier transform or Fourier series on this, you get the various frequency components, and then if you process these frequency components, you remove maybe some of the frequencies and you apply inverse Fourier transform, you will get a filtered signal. This is how noise is removed from the signals using filtering basically. Okay, this is what is basically what is frequency analysis. So frequency analysis means you're using a mathematical tool to find out that what are the frequencies available in the signal. And when you say spectrum and your spectrum estimation means you are using basically an actual device. Okay, you are using a physical device to find out the frequency content in the signal. Okay, so that is basically spectrum analyzer. So spectrum analyzer is a physical device which is used to find the spectrum of the signal. Okay, which displays the spectrum of the signal. So by spectrum of the signal, you simply means the various frequencies of the signal. Okay, and the frequencies simply means either the complex exponential signals or the sinusoidal signals. Right? This is what is the basic concept of the Fourier series. Okay, it means when we have discussed these complex exponential signals, e raised to power j omega naught t, or this cos omega naught t. We have discussed there what is the significance of these two signals. Okay, because they are acting as the building blocks. Because any signal can be generated from these signals, any periodic signal in fact, and that is what is basically done by the Fourier series. Okay, and how that was done, we have seen that the signal is periodic with a time period which is 2 pi by omega naught, and then we have defined a class of harmonic signals e raised to power j k omega naught t. All these signals, they have frequency which is the multiple of a single frequency, that is omega naught. So you have one signal phi 1 t which is e raised to power j omega naught t. Then you have another signal phi of 2t which is e raised to power j 2 omega naught t, and so on. So this signal has a frequency omega naught, it has a frequency 2 omega naught, next we'll have a frequency 3 omega naught, and so on. So these signals are called as harmonic signals. Okay, so this signal has a period which was 2 pi by omega naught. This has a time period which is 2 pi by 2 omega naught. The next signal is 2 pi by 3 omega naught, and so on. And they have a common time period that is 2 pi by omega naught. So if you combine all these signals together, if I combine all the signals, complex harmonic signals, okay, from minus to plus infinity, what I get at the output is a periodic signal. Okay, and you multiply this with a coefficient ak, which is called as Fourier series coefficient. So this representation is nothing but the Fourier series representation. Okay, so when you decompose any signal xt, which is periodic signal, in this form, the form of complex harmonics only, that is called its Fourier series. Okay, and for k is equal to 0, you are getting a0, which is a constant. For k is equal to 1 and minus 1, both will have a frequency of omega naught. In one case it will be plus j omega naught, in one case it is minus j omega naught. So those two components, they are called as, it means a1 and a minus 1, these two coefficients, this is called as the fundamental frequency or the first harmonic. Okay, similarly for k is equal to plus minus 2, that is a2 and a minus 2, that becomes your second harmonics, and so on. Okay, so in general for k is equal to n, k is equal to plus n and minus n, these two components, they are called as the nth harmonics. So any signal xt which is periodic, if you can decompose this signal in this form, that becomes its Fourier series. Okay, and let us have an example on this, a basic example. Suppose here you have periodic signal xt which is generated using complex exponentials, and it has suppose 3 harmonics, k is equal to minus 2 plus 3 ak e raised to power j k omega naught, and omega naught, suppose I take 2 pi t. Okay, it means it is a periodic signal with the frequency of or time period of 2 pi by omega naught. Omega naught in this case is 2, so it is 2 pi by 2 pi, it is 1 second. Okay, and we have some constants. Suppose a naught is equal to 1, a1 is equal to a of minus 1 is equal to 1 by 4, a2 is equal to a of minus 2, that is suppose 1 by 2, and a3 is equal to a of minus 3, that is suppose 1 by 3. Okay, these are the coefficients. So if you expand this equation xt, you can write it as, first is constant a naught plus a1 e raised to power j 2 pi t, because k is 1, then plus a minus 1 e raised to power minus j 2 pi t. Similarly, a2 e raised to power j 4 pi t, case 2, plus a minus 2 e raised to power minus j 4 pi t, and last is a3 e raised to power j 6 pi t, and case 3, plus a minus 3 e raised to power minus j 6 pi t, and a naught is 1, and since a1 and a minus 1 they are both same, which is equal to 1 by 4, so I can take it as common 1 by 4. What you will get inside? E raised to power j 2 pi t plus e raised to power j minus 2 pi t. So if I divide this with 2 and multiply with 2, this will become a cosine function, isn't it? And similarly, a2 and a minus 2, they are same. I can take 1 by 2 as common. So you'll get e raised to power j 4 pi t plus e raised to power minus j 4 pi t. And if I divide this again with 2 and multiply here with 2, this will become a cosine function again. And similarly, in the last case, a3, which is 1 by 3, and e raised to power j 6 pi t plus e raised to power minus j 6 pi t, and divide with 2 and multiply with 2. Okay, so what you get xt, you get 1 plus 1 by 2 cos of 2 pi t plus 2 by 2 is 1 cos of 4 pi t plus 2 by 3 cos of 6 pi t. So this series can also be written like this. So this is alternate extensive form of Fourier series. Okay, and from this equation you can easily interpret how the harmonics they build the signal. Okay, so you have a signal, you had a series xt is equal to k from minus 3 to plus 3 a k e raised to power j 2 pi kt, and with some assumptions of ak, we finally got this equation in the form of 1 plus 1 by 2 cos 2 pi t plus cos 4 pi t plus 2 by 3 cos 6 pi t. Now see how this signal is built from this. Okay, this is one signal, I can say it is x naught t. This is another signal which is supposed to take x1 t, this is x2 t, and this is my x3 t. So x naught is equal to 1, which is a constant signal. It is 1 for every value of t. x1 t, it is a cosine function with the amplitude of 1 by 2 and a frequency of 2 pi. So time period for this is 2 pi by 2 pi, that is 1. Okay, so the amplitude of phase is 0, so magnitude is 1 by 2, and if you plot it, you get a signal like this. This is x1 t. Okay, and similarly your x2 t, it has a magnitude of 1, the frequency is double, the time period will be half. Okay, so its time period will be half, or the frequency will be double as compared to your this x2 t. The amplitude is 1, and then your last signal x3 t, which is having a frequency thrice of this 2 pi, so time period will be 1 by 3. Okay, so it will have more highest oscillations, and amplitude is 2 by 3. Now if you combine all the signals together, if you combine the first two signals only, x1 naught t plus x1 t, what I will get? This is x1 t, this is x0 t. X0 t is simply 1. So if you add this with this, what will happen? The DC level of this signal x1 t will be shifted up. Okay, because 1 is added to the entire signal. So if you simply plot x0 t plus x1 t, this is 1 by 2, it is minus 1 by 2 here. So 1 will be added, 1 by 2 will go to 1 by 2 plus 1, 3 by 2, and this will go to minus 1 by 2. Okay, so DC level is basically shifted by 1. So it will be like this. Your function will become like this. Isn't it? This point is basically now 1. So it is minus 1 by 2 here, and it is 3 by 2 here. And then if you add x2t to this signal, so this signal x2t, if you add this with this x0 plus x1t, you will get a different signal. Okay, so that may be like this. Suppose this is suppose your x0 t plus x1t plus x2t, and finally if you add x3t with this part, that is sum of all the 4 signals, you will get a periodic signal. So that signal may be look like this. It will be periodic again, and the time period of this signal xt will be the same as the fundamental time period of this signal. Okay, so this signal has a fundamental time period of 1 seconds because fundamental frequency is 2 pi. Okay, now what we have done, we have taken example and we have generated some harmonics, and we have seen that how the harmonics they add it together to build a periodic signal, this signal. Okay, now what is the problem in the Fourier series? The problem in the Fourier series is that if this signal is given to you, which is a periodic signal, so you have to decompose this signal in the form of this series or in the form of this series. This is what is done by the Fourier series. So when you apply the Fourier series on this signal, you will get this part. You will get this expansion basically, or this expansion. Okay, it means using the Fourier series, you will be able to find that okay, this signal has a constant term which is 1. It has a first harmonic cos 2 pi t with a magnitude of 1 by 2. Then it has another frequency 4 pi with the amplitude of 1. Then it has one more frequency 6 pi with the magnitude of 2 by 3. Okay, this is what is basically done by the Fourier series. So if any periodic signal is given to you, maybe in this form, and if you want to find, if I ask you find the frequency in the signal, what are the frequencies present in the signal, how can you find? If you have a simple sine wave or a cosine wave, and if I ask you that what is the frequency of this signal, you can simply find what is the time period, and the frequency will be nothing but 1 by t. But if this signal is given to you and you have to find what is the frequency in the signal, now this signal does not have a single frequency, it is a mixture of different frequencies. Okay, and how to find those frequencies which basically build this signal? For that you have to apply Fourier series on this. If I apply the Fourier series on this, I will get the various frequencies which are present in the signal. So one may be your constant signal, then you have one frequency sine or cosine function which has a frequency which is equal to the fundamental frequency of this signal. So what is the fundamental frequency of this signal? For that you have to find the time period. This is much the time period t. So what is omega naught? That is 2 pi by t. This is how we get the fundamental frequency in the signal. It means when you write the Fourier series for this signal will contain only those frequencies which are the multiple of this omega naught. So you have one frequency omega naught, then you will have another frequency with 2 omega naught, constant component, then one more frequency that will be 3 omega naught, and so on. Okay, and when you add all these frequencies together, what you will get? Back the original signal. This is what is done by the Fourier series. Okay, so this is the basic concept of Fourier series, how I use the Fourier series for frequency analysis. So a periodic signal will be given to you, and when you apply the Fourier series on that signal, you basically try to extract the various frequencies which are present in the signal. Okay, and if you combine all those frequencies together, you will get back the original signal. And the difference between the Fourier series and Fourier transform is that Fourier transform is basically used for signals which are aperiodic, which are not periodic. And the frequency, your Fourier series is basically generally used for periodic signals. Okay, but later on you will see that your Fourier transform is a unified tool which can be used for periodic as well as aperiodic signals. Okay, so we will develop the mathematical background for this in the next lectures, and this is a very interesting topic. You will definitely love it. Okay, but I have given you a basic insight about what actually Fourier series is, okay, and why we use it.